hi everybody. Didn't expect so many people actually. I expected something less, like from what I heard. So this is my first time participating in this TED event. So I heard like usually there are less people, now much more, which is great. So I'm glad. You guys have some handouts already sorted out, so it's gonna be the main part of the whole lecture thing. So the full problem that you're gonna see through this one, it's like, I guess it's a little bit more complicated than you probably would handle, but I'm gonna let you through, okay? It's gonna be about actually cryptography a little bit, and then what we're gonna do at the end or towards those papers that you just have, so those handouts, you're gonna be a little bit part of the presentation. We're gonna have a little game at the end, so towards the end of the problem, we're gonna break a little cipher, and then you're gonna be involved, okay? So I think it's time to start. Let's see, I'm always used to like watching a clock once I'm like basically teaching lectures. I long distance, but I seeing that one, so I'm gonna go with that one. So I think it's better now. Okay, so if somebody didn't hear me from the back now, you maybe can hear me better. All right, so at the beginning, I'm gonna like a little bit say some facts and history facts and the connections between mathematics and other subjects. And then we're gonna turn into that one of the application which is related to the problem that you have in front of you, or many of you have in front of you. Okay, so all my notes that you're gonna see here, basically my own work, part of my own work on a whiteboard. So that's what you're gonna see. I took pictures and I edited them not to have all the backgrounds, and then all of these were part of my previous presentations, researches, stuff like that. Okay, so you guys, I think your level of mathematics is somewhere around like good algebra. Can I assume that? Pre-calculus, maybe little bit. Pre-calculus. Raise your hands. Okay, good. How about calculus? Little bit calculus. Nah, that's good. Now I'm home. Truly, I am. Okay, so let's a little bit start. And so mathematics is basically, so the main topic now here is to talk about the different subjects that the different like professors present today and the connection with technology. Okay, so mathematics, from my point of view, is part of all the like basically all the technologies and all the other subjects that you hearing your lectures about today. Okay, so always so mathematics as a big like building block of everything. So it has connection with all the other subjects, including chemistry, physics for sure. So you're measuring basically the substances once you're dealing with the chemical stuff and all those things. So there are some like obvious connections. But I think if I'm talking about the technology, the most obvious one is the computer science, because computer science, or through computer science, mathematics is a big building block for computer codes, writing computer codes, and through computer codes, different softwares are developed and distributed through so many different areas of different subjects. For example, like including music, including even CNC machinery, so basically the industrial field, and then also all the different softwares that basically build through the codes, and then the mathematics are there basically everywhere that you can see. Like for example, like you having all those long codes written in computer science, and they are govern those machines that responsible for making small parts of airplanes. I was working with them for a while, a little bit longer time ago, and like even for the smallest part to be made, like there must be a very, very complex mathematical code written, so many long lines of codes. And then just think about it, if one semicolon is making wrong in a long like code, the whole thing blows off. So then to debug the whole system, it takes you maybe 2 or 3 days, and only those people that have some passion for this subject would be able to do that. Otherwise you go crazy and you're gonna leave the field. So literally as it is. For mathematics, you have to have some passion to be able to work in this field. That's one of the main things that I realized through my studies, and then also through my works, and then through my researches. And so the math itself, mathematics is part of so many different like development, as most of you know, and probably everyone knows. But on the other hand, once you start to think about mathematics and work about mathematics, you basically like as that, okay, if it's that advanced, then how can I proceed in it? So like you will need a lot of machinery, you will need like computer codes, and that is not true. To start to work on mathematics, the only thing that you always need is a pencil and a paper and maybe a basic calculator. That's all that you need. And then you start to work with all those long and crazy equations, and then developing like new ideas, or part of like basically working part of as researchers try to develop new ideas or refreshing the old ones, especially in the calculus fields, um, linear algebra fields, using matrices, some of the part that we're gonna see today. And so basically you think about it like you work on your papers with your pencils and pens, and then you just start to work about mathematics, and whatever you're doing can turn into something that will develop a new technological software, maybe, for example. Okay, and that's true as it is. And then the whole thing will be turned into codes, and then will turn into computer programs, softwares, and then new systems will be developed and will be used through different areas, even areas that you wouldn't maybe imagine. Like for example, music is one of the categories, because like if you're a learner of music like I was before, but you're really a beginner, there I am really a beginner, then you try to use some software that is actually built for those who are actually beginners in music, like Guitar Pro. Why not? If some of you like to try to study new instruments. And actually, like the whole thing, the whole code for that program depends on also mathematics. And like once you're writing simple musical notes, you have to still use like at least simple amount of fraction addition, for example. So it builds from that beginnings up to writing those very long codes, and then you have to teach the system how to operate. So the system needs to know all those kind of mathematical codes, libraries, for the computer languages like R, C sharp, C++, so on and so forth. And whoever creates the original program has to teach the program for a library. So once you're writing your code, I don't know how many are you did at least the beginning computer coding class, beginning C sharp, C++, something like that. Okay, good. So one of the best that I like before is the C sharp, because that works with the very basic. So that's old one. But if it's older one, then you need to go back to the beginning to be able to start building your code. And then you just assume that like, okay, once you start to write your code, the computer code, so like the C sharp or the C++, knows everything. And it does, because somebody already developed it. So once you plug in a cosine function, then and you want to do an evaluation on the cosine function using the code, the program itself knows what to do, because it's already programmed. And to be programmed, mathematics are used there. Okay, so let me maybe start, and let's have a little connection now with history. So a little bit history part, history lecture. You're gonna see, so let's see the next part. So these are my own notes that I just used recently. This is something, so what I really wanna share here. Let me see if I can escape from this. Okay. And then do we have not here, right? This one, okay. So like once you're gonna use computer algebra systems for your studies to be able to calculate like more complex calculations, if you're gonna go into higher mathematics, then think about it like one of my favorite one is the Wolfram Alpha, and I just wanna show you something very quickly. So you can use Mathematica, Wolfram Alpha. Desmos I like the best for graphing, at least for the one-dimensional graphing. Two-dimensional graphings mostly use Mathematica or MATLAB. But let me show you, if you go to your Wolfram Alpha here, this computer algebra system can compute even very complex mathematical stuff. So for example, let's say if we want to sum from 1 to infinity of 1 over the so basically we're squaring from 1 to infinity the reciprocals of the perfect squares. Okay, and then if you do this, then you're gonna get your result How long did it take? How long did it take? Couple of seconds, right? Couple of seconds. So now the sum is pi square over 6, as you see right here, pi square over 6. And this is a famous result. This is the so-called Basel problem from 1656. And French mathematician, I can't recall the name at this time right now, but the French mathematician came up with the problem. Okay, we know that this infinite series converges, but where does it converge to? So we have no idea. And then he started to work on the problem from 1656. And first time Euler, the very famous, I think one of the most famous mathematician, one of my favorite ones, solved the problem in 1734, so it took almost like, let's say, I would say 70, 80 years. And then first was published in 1735, December 5th, so it's almost birthday for that. So basically now, in nowadays, you just have this Wolfram alpha, even Mathematica, other computer algebra systems, you plug this result, you plug the question in. We know that this series converges by the P-series test. If you're going to take integral calculus, you're going to know that. But then you will not study where it converges. That's a really hard problem to come up with. Then you use the system, took 5 seconds, as like you said. Okay, good. Now let's back to here. I worked on this problem and proved this problem 5 different ways. I'm not going to show all the 5 different ways to you, but let me maybe click right here, going back to, how can I make the slideshow out of this? That's okay, you still see. So anyway, like I worked on this one. So I basically proved this result 5 different ways. This is not the most common approach. The most common approach would be the Parseval's identity, but still this is a very nice approach that I like, including complex variables, complex numbers, and including like advanced calculus and a little bit of number theory once we switching, actually a little bit of real analysis once we're switching the integral sign and then the summation sign. So this is the first part. I worked on this one like maybe 3-4 weeks ago. I think it's a 3-4 week ago work, and then here is your result. So basically the whole part like turns into your infinite sum. Anyway, I'm not gonna go through the details. That's not part of the thing that I want to talk about, but I just wanted to show you that this is one way to prove this result. Took me maybe like, I would say 2 hours after knowing the steps, but with the research, how to see the steps, took me like more. And then if you use your Wolfram for other systems, it took you 5 seconds, right? So what is the beauty in that? Like really, I'm talking about like Wolfram alpha, Mathematica, and all these like computer algebra systems are very nice to be there because you're gonna use them in your studies. If you're gonna get into universities and higher educational stuff, they are more than helpful, like super helpful, even more than super helpful. You will know that. But if you want to see the background, you wanna get your hands dirty in mathematics. So that's the main idea, okay? So you want to really, really work on the problems deeply. And then once you're gonna have your result, then you're gonna be satisfied. Okay, now basically I'm just using the computer algebra system to check whether my result is correct. See? And then if you're working on maybe like a very long, couple page long problem and you're missing up your calculation somewhere, just because of a negative sign went wrong, then you're gonna be pissed off and then you're gonna go back. And then if you're really gonna have passion about logic and mathematics, you're gonna appreciate all those mistakes and how you correct them on your own. Okay, so that's one of the main things I wanted to share through this. And then next is another example. I'm not gonna go through too much on that one because we just like would have more, advanced mathematical stuff. But I'm gonna mention a couple information about the next the next formula that we have. This is the so-called Wallis product. And this was part of my very long presentation 3-4 years ago. I used it like one result. I had 2 main results. And the idea, the beauty of this thing is the following. So Wallis, he was an English mathematician from UK, and then he proposed this Wallis product. So he proposed this result for the value of pi over 2 back to the beginning of 1650, so close to the other result. Okay, close to the other result. Now, somehow he came up with the idea, he worked on it, he proved the result, and nowadays the most common proof, as you see here, involves calculus. And calculus was not advanced up to the last, let's say, 60, 70 years, okay? So now think about it, like 400 years ago, almost 400 years ago, this guy figured out this result, proved it on his ways, going back to like, almost back to the medieval times. Like think about it, what he could use, like, paper, pencil, no calculator, then nothing. He proved the result, and he didn't even have calculus to prove the thing. Okay, so now we're using, like almost 400 years later, we're using calculus to prove this result. We have used the cosine extension, and then you can see the steps that I'm not gonna talk about again. The steps, I'm just like wanted to give you a hint how like mathematics were developed through the, I wouldn't even say centuries, through thousands of years. Okay, I don't know if you know that your famous quadratic formula. You dealt with that. How many of you dealt with that? So how old is that thing? How old is your famous quadratic formula? Anybody? Make a guess. Somebody raise your hand. Make a guess. It is 4,000 years old. It is 4,000 years old. Okay, and the beauty in the all these like old year this old stuff, that like you can still prove the same result. So it is already proven. If in mathematics you came up with a hypothesis and then you make a conjecture out of it, then it's proposed to be a theorem. If somebody can prove that to be a theorem, then it's called a theorem. So it needs to be proven fully. So there are at least 7 famous problems nowadays that you could prove. The last one, actually it's only 6, because the last one, the Poincare conjecture, was proved back to 2002. But if you would be able to prove any of these, one of the most famous one is the Riemann hypothesis. It's still not proven. If you can prove it, and it's already proven for a million times that it's not proven enough to be taken into a theorem. And if some of you would be able to prove it today, present it, and then a group of mathematics, I think from the MIT University, I think they are the one who are actually giving out the prize for that. You could win $1 million, literally. Okay, you can check up the list. It's called the millennial problems, and there are still 6 open, and there are some others, but the 6 ones, especially the Riemann hypothesis, is the most famous one. Okay, so anyway, going back to 1655, the guys came up with this, and then 400 years now later on, we use calculus to prove it, and then we can say, like, it's a history, like fact, maybe that, okay, like 400 years ago, that guy was correct. Maybe he didn't know what to do with this, but he was correct that time. And much more crazy about this result, in I guess 2019 or so, but definitely during the last 6-7 years, some university students, chemistry students at, I think at the Michigan University was, but I can't recall that. They figured that this product has connection with the hydrogen atoms movement. So it has connection with the hydrogen atoms physical property, even crazier. So, all right, let's move on before you just like get involved this so many mathematical concepts here. So basically, this was part of my presentation. This goes on, and then finally the result is right there. And one more comment about this one, and then we're gonna jump into our long problem that I mentioned. Is the following, that it's a very nice result that I really like, that using the Wallis product and then using a very, very close sum to it, you can write down a very nice formula for the pi value. What is pi? Anybody? It is not 3.14. It is 3.141592 and so on and so forth. It is an irrational number, and then one of the so how you can represent irrational numbers? Anybody? It's not a proof that that number is irrational, but definitely a representation. You're gonna have infinitely many decimals, but you have to have no pattern, no repeated pattern. If you have any repeated pattern, even if it starts to repeat after the 1000th place, it's still rational. Okay? So the pi has the infinitely many, and I'm telling you, if you would go back to the Wolfram alpha, I will not go back to that, and then you would say that you would like to see the first 10,000 digits, guaranteed, you're gonna take your time, you're gonna not find any single repeated part showing that guy is truly irrational. Okay? All right, so now let's get into that problem that I mentioned. So one of the technological connection between mathematics and computer science actually is code breaking, and now we're talking about ciphers and cryptography. I didn't work in that field, but I studied long enough that I present one problem, and the problem that some of you have in front of you, is going to be part of that code breaking problem that we go. So let me open that. This is where we start. Actually, I had this problem figured I basically constructed the problem around a year ago or so and used this as presentation for one of my classes. But like I literally did this problem for you like 2 or 3 days ago, and I color coded the steps and stuff like that. Okay, so let's go through the main steps before we can get to that part where you will participate in your notes. Okay, so you will need something to write with. Pen, pencil, doesn't matter, but you need something to write with. You have your paper, and you're gonna need some calculators. Okay, you're gonna need some calculators. Even your cell phone make it. Okay, but at first let's go through the problem and let's go through the steps. So we want to decrypt the following cipher. So I created this cipher. You have -5, 67, 9. As you see the numbers, I'm not gonna read them. They are on the not whiteboard now, but basically whiteboard. Okay, so they are right there. And you have 9 of them. So the message that we are sharing here is a 9 number message actually originally, but it's actually a 9 letter message. So this could be turned into a letter. Now, the English alphabet has 26 letters, right? 26 letters. From A to Z, you have 1 through 26. And if you try to match all these numbers with any of them, it would make no sense. You can't even do that for most of the times. Think about the first ones. -5, you cannot have -5 for a letter corresponding to -5, and then 67, it's greater definitely than 26, so it doesn't make originally sense. This message is decrypted. Okay, no, sorry, this message is encrypted. This is the one that we want to decrypt. So now it doesn't make any sense, and we want to make sense of it. Okay, so to be able to make sense of a message that is already encrypted, you need to have the tool that the original encryptor used. Okay, so whoever encrypted the message, if you don't have that tool, therefore it's hard to break codes. Going back to, let's say, maybe the war times, back to the Second World War, and so on and so forth. The hardness of breaking the code is not like breaking it if you already have what was used, because whatever was used is basically just need to be inversed. So basically we need to make the opposite, we need to find the opposite operation for that process, whatever was used to encrypt the message. Okay, makes sense? So basically you have a tool, you had a tool, you use that tool to encrypt your message, and then you send it to somebody. And now if that somebody will not understand it if cannot have your key to it, what you used. Okay, and whatever you used, it has to have an inverse, and then you have to find that inverse, and using that inverse you basically reversing your process to go back to your original message. Okay, so let's jump into it and let's see what we're gonna have for this. So with decrypt, we're gonna decrypt this message, this encrypted message, and here we're using a 3x3 matrix for it. Okay, so here we're using a 3x3 matrix for it. All right, so to be able to use it, at first we have to a little bit recall matrix vector multiplication. This is a simple process. Once you're gonna be there, this is a really simple process. You have the matrix A that was used, that the matrix from the previous slide that was used for the encryption, and then we multiply these X vectors with the 3x3 matrix to encrypt the message, and then we're getting new vectors, these V vectors right here. Now, if you have a 3x3 matrix, then the corresponding vector must be 3x1. Otherwise, the matrix vector multiplication in this case doesn't make sense. You can't proceed. So for matrix multiplication and vector multiplication, you have to have certain property of the multiplication for the given matrix and for the given vector for the multiplication to make sense. And that connection is, you have a 3x3 matrix, and now we have a 3x1 vector. Your second number for the matrix and first number for the vectors. So basically, the column number for the matrix and the row number for the vector must match. Otherwise, you can multiply. Okay, so this message here must, whatever message you're gonna make using this way, it must have a number of letters that is a multiple of 3. Otherwise, you can make it. Okay, it's only gonna work with messages that are multiples of 3 letters consist of. Okay, all right. So we have the 3 by 3 matrix that we saw, and then we have the decrypted message. That's what we want. We want to solve for x. That's usual for mathematics. You want to solve for x, but now we're going to solve for x vectors, 3 of them. And then, so the original 3 x vectors were used to encrypt the message. So the original decrypted message is the x, what we want. We pre-multiply it with a, and then we are getting the v vectors as you see right here on the right side. So basically turning your 9 number long message into 3 by 1 vectors. That's what we have. So this is your encrypted message. All right. So now to be able to do the decryption, so to be able to make sense of it, then, okay, let me go further. Then we have to find the inverse operation. So for matrices, it's called the matrix inverse. If you would use functions, that would be a simple process. I'm gonna get to the end, so I'm gonna have a very short example like this, but that's way easier than this one. You could use function inverses if you use originally functions to encrypt a message, but the only thing that you have to make sure that the inverse exists. If the inverse doesn't exist, you cannot do the whole process, okay? So for matrices, the inverse process that we want to use is the matrix inverse. So we want to pre-multiply both sides of the equation with the matrix inverse. So we have to find that 3 by 3 matrix inverse. That's basically the key to the problem. If your receiver don't know the matrix that you used, the probe cannot be broken. Okay, so that's the idea. So we need to have this 3 by 3 matrix inverse. That is a 5-step process to go through. And step number 1, we need to calculate the so-called determinant of the original matrix A, okay? And this is the original way. This is not the only way that you can find the determinant of a matrix. There are at least 4 different ways. This is the official so-called expansion, the long expansion formula for determinants. And basically, I'm expanded this along the first row and used the formula itself. So basically there is an alternation of a negative sign for the first part, where for the exponents you're summing the given row plus column number. Okay, so think about I'll just give you a very quick example. For the first element, you have your 3 rows, you have your 3 columns. So the first element is the first element in the first row and also the first element in the first column. So it marked with A11. A11, the notation 11 tells you the first number, 1 tells you the row number, and then the second number tells you the column number. Okay, so then you're summing the row number and the column number for the exponent of -1 to see how the sign alternates for the given part. So once I'm expanding along the first row, I need to use 3 sub-matrices. I'm gonna have -1 multiply -1 on the power of the row number plus column number times the element itself, which is 1, and then the determinant of the corresponding 2 by 2 matrix in the down corner right there. Okay, so I color coded it enough, hopefully, for you to see how it carried out. Okay, so the 2 by 2 matrix that you see on the right is the 2 by 2 that I just marked in the lower corner right there with red color, and then you have black, and then you have green colors for the other 2 matrices. Okay, all right, so this is step 1. And then let me move on to step 2. Step 2, we're finding the so-called matrix of minors. So here what we're finding 2 by 2 matrices determinants. Let me go back to here for a second. This definition tells you that the determinant of a 2 by 2 matrix is, so if you have a 2 by 2 matrix, then you multiply the main diagonals and then subtract the product of the anti-diagonal entries. So basically, if you have A, B, C, D, then the determinant of B is AD minus BC. Okay. So using this, we're gonna find in the step number 2 matrix of minors. So here we're gonna have 9 different determinants to be counted. So basically 9 determinants of 9 2 by 2 matrices. Okay, and then let's maybe just have one example and the 9 follows from that. Talk about the very first element again. So the first element in the first row and then also in the first column. So element A11 that corresponds to or will be replaced by the determinant of the 2 by 2 matrix in that lower corner. So basically you can think of, you're gonna cross out your first row, you're gonna cross out your first column, and then you're gonna take the determinant of that little 2 by 2 matrix there, and whatever the determinant is, that will replace the element A11. So we're going from the matrix A to the matrix M. Okay, you can see the process. The first element A11 is replaced with the new element A11 in the second matrix, so that's going to be -3, and that -3 is the determinant of that corresponding little 2 by 2 matrix in the lower corner. Okay, and then if you looking for the new element for A21, so the second row and first column element that I marked with black, then you have originally number 2. So the corresponding matrix, the small matrix, is going to be 2 minus 1, 2, 1. And then you're going to calculate the determinant of that, which is going to be that, let's see, -4. So you have 2 times 1 along the main diagonal minus 2 times -1 along the anti-diagonal. So that is, again, AD minus BC. So then at the end, you have 2 plus 2, which is 4. And then so on and so forth. You're replacing the new you're replacing all the elements with the new 9 elements. Okay, and then once we have the matrix of minors, then we're gonna find the matrix of cofactors. I called it C standing for cofactors. And then what we have for this cofactor matrix, this is a simple step. Step number 3 and step number 4 are pretty simple. Like here, the only thing that you do, you're gonna change the signs of in the first row, second column entry, and then the second column, first entry. So wherever the sum of the row and wherever the row and the column sum adds up to a odd number, there we're gonna have a sign negation. Okay, and then we're gonna get this cofactor matrix. And then we go into step 4, where we want to find the adjoint matrix. Now, the adjoint matrix is the so-called transpose of the previous step. The transpose of a matrix is basically you're replacing the columns by its rows. Okay, so exchanging rows and columns. In this case, if you exchange them, you're gonna have exactly the same matrix. That's not true most of the time. In this case, it's true. And then if it's true, then such a matrix is called symmetric. So a matrix is called symmetric if it's equal with its own transpose. All right. Then finally, step 5 to finding our wanted key, the A inverse. You have this previous step matrix. So after we change the signs that needed to be changed, after finding the transpose, then we pre-multiply this 3 by 3 matrix with we pre-multiply with the reciprocal of the determinant of the original matrix, which we found back to the step number 1. And all these long processes gives you the key A inverse to now finally break the code. Okay, so now let's see what we have. So now that we have the A inverse found through these long steps, then now we got the key to break the cipher. And then the only thing that we want to do to multiply all the 3 encrypted vectors, pre-multiply them with this A minus, and then you're gonna get 3 new vectors. Those gonna be the encrypted one. Those gonna be the ones that you will be able to match with one letter from the English alphabet, and then finally get your message that will make sense. Okay? All right, so everything is summarized here. So we got now our tool, which is A inverse, and then you have the decrypted message that we want to get. So basically finding the X finally. We're gonna get it in 3 pieces for the 3 X vectors. And then we're gonna find it by pre-multiplying the V vectors by this A minus that we just found through the long process. All right, so all the V1, V2, and V vectors, the V1, V2, and V3 vectors are copied over right here. So this is, again, the encrypted message that we have. This is the one that we want to decrypt, okay? So let's start on that one. This is a summary, again, the whole thing. So let me just go on. So this is what we have at this time, and now it's time to break the code. All right, so now this is the first slide that you should have, or some of you should have in front of you, okay? So basically, you just have to participate in the short and easy part, multiplication and addition, that's all that you will have. So let's see how it will be carried out. So for the first vector that we're gonna decrypt is gonna be the V1. So we will pre-multiply it with the A inverse matrix, as we said. So we have this pre-multiplier of -1/16 that's gonna stay till the end. So we're gonna use it in the very last step. And then you have your A inverse all together here. And then the red column vector right here is the V1, the encrypted one that we want to decrypt now. So how the matrix vector multiplication works, you multiply with your first element, you're gonna multiply your first column, and then with the middle element, you're gonna multiply your second column with, and then with your third element, you will multiply your third column with, okay? So even very detailed out in the next step. So I think I'm using baby steps here, but I've detailed it out and color coded as much as I could, okay? I was working on after midnight here on campus, so please, keep with that. Okay, so what you will have to do in this next step to carry out the multiplication, simple as it is, multiply out and then write in your green columns what you're gonna get, okay? So maybe I'm gonna give you a little time. Actually, I need to see the time. We have around 40s, and my computer can, okay, good. All right, so multiply them out, and then let's see what you're gonna get. So basically, you have -5 times -3, then you're gonna have -5 times -4, and then you're gonna have -5 times +5, and then you're gonna have your first column, okay? And then for the second one, 67 times -4, and then times 0. That's maybe the easiest one, right? And then times -4 again. So the first element in that vector gonna be the same as the last element. And then you're gonna pre-multiply the last vector with +9. Okay? So get what you just carry out your multiplications, okay? Just kind of raise your hands or knock your heads or say that you're ready if you're ready. You ready? Here guys, ready? I'm gonna check like groups because so many of you right here. So you guys ready? Who's not ready? Okay, so you can check if you got correct or not. In the next step, you're gonna have your results right there. Actually, if some of you already wanted to cheat, it's on your second page. So for the first one, I included the steps like page by page, but it's not gonna be true for the second and for the third one, okay? Then you're gonna have to make the full work. Okay, so how many of you get it correct? Or some of them correct? Good, okay. So I basically breaking down the very long, very complicated problem into easier parts that you can participate into. That's what we're doing to finally get this message. Okay, so next step is to basically carry out the additions. So once you have 3 row vectors next to each other with the same size and you want to add them, you can add them, okay? You can only add vectors of the same size. If you would have different sizes, you cannot add, but these are definitely no problems. So I even took them together in the addition. So that's really an intermediate step that I usually don't carry out once I'm taking care of these long additions, but I put them together in for you in that like 3x1 long addition on the right, okay? So now you want to do the addition/subtractions through those rows, okay? You did? Okay. You ready? Done? If we can wait there. Okay. So this is what you have. How many got you correct? Check. Good, good. Okay. And then the last step is to bring the negative 1 over 16 in and then divide all the elements with negative 1 over 16. Okay? All of them will be divisible. Okay? So divide them out. So you're doing easy steps, but if you would think about the background, like all these numbers that you're getting after these so-called linear combinations, they must be divisible by 16. Otherwise, if they are not, you will not get integers. If you will not get integers, you cannot match them with numbers from the alphabet. You cannot say that you have 1.5 equal with something in the alphabet. You want to have numbers between 1 and 26. That's number 2. So you cannot have negatives. So all the entries must be negatives in the final column because the negative 1 over 16 after the multiplication will negate the sign and therefore your result is going to turn into positive. Okay? If you would get negatives, you're wrong. You can't match with numbers, right? And once you get your positives, those values must be between 1 and 26 all the time. Otherwise, the message doesn't make any sense still, right? Okay, so you're done with the divisions? Right? Good, good. Okay. So let's see what we're getting. We're getting this result here. Okay. You got that? Okay. So we have 13, 1, and 20. This is going to be the first part of the message. And then we're going to have 2 more multiplications to carry out. So now I only included the main, like the first page for you, basically, which is this one. And now you know the steps. So now you're gonna carry out all those, okay? And then get your second vector. So I'm gonna wait a little bit now, okay? So do your multiplications, do your additions. You can skip the intermediate step if you want to because you know that you have to add or subtract. Just basically the intermediate step tells you that you're allowed to do the addition and subtraction if you have the same size of vectors. And then once you carried out all those, then you will still have to bring in the reciprocal of the determinant of the original matrix A and then get your final result. Okay? How many of you ready? Okay. Okay. You good? How many of you ready? You ready? Right here? Some of you here? Okay, so let's turn it into let me just go have the steps. You have these ones correct, right? And then you have these ones correct. And then you have the final ones correct. Okay? So now we have one more to go. Okay? We have one more to go. And then on the last page that you have in front of you, you have the English alphabet with the corresponding 26 letters. So now it's time to finally get your final message. So basically get the third part. And then, there you go. You went ahead, but I wanted to say that let's make it like a little bit more interesting. So for the 3 fastest one, I have some gifts. So you got to first. Who comes second? Second. Waiting for a third one. Who else got this one? Whoever comes here can come as third. Anybody? Somewhere on the back, you have it? Okay, so I'm asking you I saw the first one, trust in the second one, asking you, so what is the final message? There you go. You're good. So let's go and just finish it up. So you have your third part. And then once you have your third part, then you have your final cipher broken right here, put back in the raw form, and then the English alphabet that you have in front of you with the corresponding letters, and then the message, and the message is broken. Okay? So at the very end, today's message was only this. From me to you.